When we're working with virtual machines in terms of CPU, we can obviously create virtual machines with as many virtual CPUs as we have logical cores on our ESXi host. I can create virtual machines with 1 vCPU. I can create virtual machines with 2 or 4 or 8 or 16 vCPUs. I can pretty much go as high as my hardware will allow me to go. The rule being is that when a virtual machine wants to schedule threads, and you've got a virtual machine whose application is multiprocessor aware, then that application tries to schedule its threads across all of the virtual CPUs. As long as there's something physical on the hardware to actually execute those threads, then you're good to go. Now, this will allow us then to overcommit our CPUs in the same way that we can overcommit memory. That is, I can have more virtual CPUs allocated to my VMs across all of the VMs than I have physical cores to execute those threads, because not all of our virtual machines are executing CPU threads 100% of the time. Now, when it comes to hyperthreading, we have to be a little bit careful. Hyperthreading is actually a term coined by Intel, and AMD has a similar concept. But the idea here is that you can schedule multiple threads at the same time on the same core. 2 threads can be scheduled on the same core. Now, that doesn't mean that we can execute both of those threads at the same time. In some cases, we can. If the operations between the 2 threads that are scheduled on the same core are, for example, very different from one another. A very simple example, I've got multiplication and addition. Okay, those are my 2 threads. We can schedule those at the same time. But 2 multiplication problems, I can schedule them at the same time, but I can have to execute them one at a time. Okay, think about a toll booth. A toll collector can hand out a ticket to one car on one side of their booth, and they can take a ticket or take tolls from the other side, right? Hard to do that at the same time, right? But if they can handle both lanes, we're actually still operating a little bit more quickly. It's a little bit more efficient to do this. Now, in many cases, on the physical side, running your applications on physical hardware, you can see about a 20% performance improvement in general. But ESXi is a little bit smarter about this, and we'll show you how that works. And we can actually eke out up to about a 30% performance improvement. Now, there have been some security issues around Intel CPUs in particular related to hyperthreading, okay? And if that's something that you are concerned about, there are some patches on the ESXi side, and there are some ways that you can sort of get around some of those security issues by ensuring that a virtual machine, that no 2 separate virtual machines are scheduled on the same thread, or on the same physical core rather, at the same time. You can dive a little bit deeper into that issue, and we cover it more deeply in our Optimize and Scale course as well. But let's talk about here the requirements for this. First of all, hyperthreading has to be enabled in the system BIOS, and when that's done, ESXi will detect it. So there's nothing else that you have to do, okay? But all of this leads us to the topic of CPU load balancing. That is, how does the hypervisor determine which CPU threads coming from which virtual CPUs in which virtual machines get scheduled on which physical cores or even logical threads within the same physical core? Well, the hypervisor is really, really good at this. The first thing that the hypervisor attempts to do is to utilize the separate sockets that are available to it. So if I have a motherboard in an ESXi host with 2 sockets, and I have memory banks allocated or separated for each of those sockets, what ESXi will try to do is schedule the virtual CPU threads from virtual machines separately on each of these sockets. So one VM will be over here, and another VM will be over here. And that's great. All of the threads coming from the same virtual machine will attempt to be scheduled within the same socket. Or another way to put that is within the same NUMA, non-uniform memory access, within the same NUMA node, which is the combination of the socket and its memory. Okay? So all of the threads from one VM go over here, and all of the threads from another VM go over here. That's great. If I've got 2 NUMA nodes, I've got 2 virtual machines, everything is good to go. Now, if I've got more than 2 virtual machines, then we'll be utilizing the ESXi host will attempt to schedule other virtual machines within those same NUMA nodes on those same sockets, right, in the same way until there are no physical cores within those sockets available anymore. Now, when I'm talking about this, when I'm talking about scheduling CPU threads and executing those CPU threads, you know they happen very, very quickly. They're measured in gigahertz at this point, right? Billions of transactions per second. That's pretty fast, okay? So imagine I've got lots and lots of virtual machines all scheduling and executing very, very, very quickly. In all likelihood, there's plenty of CPU cores to go around, okay? Of course, the more virtual machines that you have running on each ESXi host, the more difficult that is to do without having to run into contention, where I've got many, many virtual CPUs, many more times the number of virtual CPUs than I have physical cores on which to schedule and execute those threads. CPU over commitment is what we are talking about here. Now, in many cases, we look at a ratio of virtual resources to physical resources. When it comes to memory, we've kind of looked at a general recommendation that you shouldn't have more than 2 gigs of memory allocated for 1 physical gig of RAM. I actually think that's really high, and the likelihood that we would be swapping in that case, where I had 2 gigs of RAM for every in the virtual side for every physical core, or for every physical gig of RAM, I think we're going to be swapping. In the case of memory, that's very different, because memory is usually more scarce than CPU in terms of our actual utilization versus the allocation. Okay? If I allocate 8 gigs of RAM, in all likelihood, I'm going to use pretty close to 8 gigs of RAM. But if I allocate 8 virtual CPUs, how often am I going to use all 8 of those virtual CPUs 100% of the time? That opportunity is a lot less likely in most cases. Of course, if you happen to have CPU heavy or operationally heavy CPU applications, well, all of that goes out the window. But in many cases, the ratio that we recommend is more like a 6 or 7 or 8 to 1 virtual CPUs for every physical core. Of course, all of that depends on the applications that you run and your own environment. Now, in the event that I have more virtual CPUs that need to be scheduled than I have physical cores, that's when hyperthreading can kick in, okay? So let's go back a slide and quickly have a look at hyperthreading here again. You'll notice that what we're attempting to do is ensure that virtual CPU threads are scheduled on separate physical cores if those virtual CPU threads are coming from the same virtual machine. And it's only if we're out of physical cores, like we're showing here, where we have this virtual CPU that needs to be scheduled. This virtual CPU will then, coming from a separate virtual machine, find a logical thread within a physical core to become scheduled. By doing this, we have a better chance that these two different threads here that are running on this logical CPU core are different from one another and therefore can actually be executed at the same time. Now, this is all well and good and had been for many years until the discovery of this issue with the Intel CPUs. Okay? So there is a setting that you can execute on the ESXi host to prevent this from happening. And instead, what we'll end up seeing, instead of this chart, what we'll see is both of these two being executed on the same physical core, and then this one executed over here. Okay, so that's the possibility of trying to avoid two virtual machines sharing the same physical core. Now, the performance here is not quite as good, okay, but it might mitigate that issue should ESXi or should one of your virtual machines become compromised, that the CPU thread be shared across across those compromised virtual machines. Okay, so that's the story of hyperthreading. Let's then continue our CPU load balancing discussion simply by saying that ESXi does a really great job of trying to balance the incoming CPU thread requests across the available ESXi, across the available physical cores, and does this so much to the point where we can overcommit by a ratio, a significant ratio, 6, 7, 8, 9, 10 to 1, without really having to worry so much about performance issues. Now, what are those performance issues? We'll discuss those in the next lesson, okay? But in the meantime, we've given you a pretty nice idea of how ESXi handles CPU and memory allocation coming from virtual machines and placing them on the physical resources that you have on the ESXi host. We know about some of those memory overcommit techniques like transparent page sharing or ballooning and compression and then swapping, right? And we understand how symmetric multiprocessing works and how ESXi handles hyperthreading. So when we come back, we're actually going to look at some resource controls. That is, can I prioritize virtual machines so that they have more prominent access to those physical resources, so that in the event that we do hit contention, the workloads that are most important to me actually get those physical resources and don't experience performance problem. We'll be right back with lesson number 2.